Welcome to this explainer. Okay, today we are stepping onto a microscopic battlefield. Seriously, deep inside the devices we use literally every single day, there is this relentless, invisible war being waged in hardware design. The ultimate mission? Saving physical space on a silicon chip without sacrificing even an ounce of operational speed. It's this massive tug-of-war between making things as tiny as physically possible and ensuring they still process information at lightning speed. We're going to look at some fascinating simulation data that tests the absolute limits of this exact trade-off. And then we'll see how completely rethinking memory might just change the rules of the game entirely.
So it begs the question, in microchip design, does fewer transistors always mean better performance? I mean, it seems completely logical, right? If you use fewer parts, the circuit is smaller, the path is shorter, and theoretically it should run faster and use way less energy. But as we're about to see through some pretty rigorous circuit simulations, this complex tug-of-war between area efficiency and raw logic performance, it holds some major surprises.
Okay, let's dive right into this. Here's our roadmap for today. First, we'll look at digital building blocks. Then, we've got a showdown, XOR-XOR versus CMOS. Third, the performance verdict. Fourth, modeling FPGA memory cells. And finally, in-memory computing.
All right, starting off with Section 1, digital building blocks. Before we can really appreciate all the crazy innovations and space-saving designs, we need to understand the absolute baseline of what these circuits are actually doing. Enter the full adder. It's exactly what it sounds like. It takes 3 binary inputs, usually A, B, and a carry in, or CN, and calculates a sum and a carry output. Why does this matter? Well, because this basic computing block is the absolute foundation of all digital signal processors, microprocessors, arithmetic logic units, the whole shebang. Every single time your computer calculates anything, it's relying on millions of these tiny adders working in perfect harmony. How efficiently they operate literally determines the power and speed of your entire system.
Moving on to Section 2, the big showdown, XOR versus CMOS. You can kind of think of this as a match between a scrappy, highly compact underdog and the undisputed heavyweight industry champion. Over in corner 1, we have the XOR-XOR 18 transistor design. This is an architecture that uses 2 XOR gates right at the core of its logic. Its entire philosophy? Minimizing transistor count and saving incredibly valuable silicon area. It's lean, it's mean. But in corner 2, we have the standard CMOS design. This is your traditional approach, using complementary NAND, NOR, and inverter logic structures. It uses a complementary arrangement of PMOS and NMOS transistors, which means it takes up more space and uses more parts. But it prioritizes robust noise margins and low static power leakage. So the stage is totally set here, ultimate compactness versus standard reliability.
Which brings us to Section 3, the performance verdict.
To figure out who actually wins this fight, both of these designs were put through some rigorous LTspice transient simulations. We're talking perfectly identical 5-volt supply conditions, using standard BS170 and BS250 transistor models just to mirror real-world device behavior as closely as possible. So, does smaller always mean faster? Let's look at the propagation delay and dynamic power metrics. Spoiler alert. The CMOS heavyweight champion wins outright. No contest. Despite actually having more transistors, the CMOS design boasts lower propagation delay, meaning it's faster, and lower dynamic power, meaning it's way more energy efficient. And honestly, this wasn't a fluke. This held true across all 16 possible logical input combinations they tested. The super compact 18 transistor design, it's just slower and burns more power.
So the really crucial point here is understanding exactly why the leaner design lost. The XOR-XOR design's downfall was essentially its need for support structures. Because the design is so stripped down, it actually required the addition of pull-down resistors just to ensure the output logic levels remained stable, especially for those low-strength signals. Think of these resistors kind of like speed bumps on a highway. They were absolutely necessary for safety, to ensure proper logic values, but these speed bumps created extra paths for power to just leak away as heat. Plus, they physically slowed down the logical transitions. Basically, the design saved space, sure, but it paid a massive, massive toll in speed and energy.
All right, pivoting to Section 4, modeling FPGA memory cells. While that whole showdown shows us the limits of shrinking traditional logic, it's definitely not the end of our story. What's incredible is that LTspice isn't just for simulating standard arithmetic adders. Its versatility allows us to literally model the future of hardware using finite-state machines. Enter the FPGA, or ferroelectric tunnel junction cell. Now, this is not your standard memory. Traditional memory just stores binary zeros and ones, off or on.
But FTJ cells, these are advanced, non-volatile memory cells whose behavior can actually be modeled as finite automata. Using the dot machine statement in LTspice, we can simulate these cells holding multiple, specific, distinct states based on the exact voltages applied to them. We are officially moving from simple on-off switches to highly dynamic, multi-state components.
To actually operate this macro cell in simulation, it has to follow some incredibly rigid sequential rules. Step 1 is a reset. A very specific negative 4.5 volts is applied to force the cell into its baseline state, which we'll call state 1. Step 2 is the write phase. A control voltage of 5 volts must be applied alongside a highly specific input voltage, and we're talking with a super tight 0.01 volt tolerance here, just to trigger a state transfer. Finally, step 3 is read. 1.5 volts is applied to safely output the stored state without accidentally overwriting it. It's this incredibly precise, delicate dance of voltages governing these complex state transitions.
Now, what's really interesting here is how we actually measure these states in the simulation. LTspice uses a brilliant little modeling trick. It attaches the output node to a 1 ohm resistor. Because the resistance is exactly 1 ohm, the output currents map directly and cleanly right to the specific memory states. So state 1 outputs 1.08 milliamps, state 2 outputs 1.44, all the way up to state 4 hitting 2.36 milliamps. This neatly proves the FTJ cell can reliably hold and output distinct programmable states way beyond just basic binary on and off.
And that brings us to our final stop, Section 5, in-memory computing.
This is where we get to connect all the dots. We take the arithmetic logic concepts from those full adders we talked about in the first section, and we combine them directly with the advanced multi-state memory we just modeled. This combo results in a true game changer, a ternary adder. Instead of being stuck in binary, this circuit adds signed digit numbers using 3 states: -1, 0, and +1. In a 4-digit ternary adder setup, the digital logic handles the very first step of the calculation, and then, okay, here is where the magic happens. The intermediate result is directly programmed into the FTJ memory cells as states S1, S2, or S3.
This whole process is achieved using behavioral voltage sources that create a literal feedback loop. The cell's current state is read. It's instantly evaluated, and that evaluation is immediately used to trigger a shift to a neighboring state. Basically, you are computing data exactly where it is stored. We aren't moving data back and forth between a processor and a separate memory chip anymore. The memory cell itself is doing the processing. It's wild.
So I want to leave you with this final thought. We started by looking at a scrappy 18-transistor adder that tried so hard to save space, but ultimately ended up losing on speed and power. But if we can move away from traditional logic gates entirely and instead compute directly within these ultra-dense multi-state FTJ memory cells through in-memory computing, what happens to the traditional barriers of microchip speed and space? By rethinking the architecture from the absolute ground up, we aren't just making existing circuits smaller, we are completely reshaping the future possibilities of VLSI systems. Thank you so much for joining me for this explainer.